Imagine an object so powerful, so mysterious that it can swallow light itself, and yet may also be the key to unlocking the ultimate secrets of the universe. For decades, black holes have been depicted as cosmic monsters, devourers of stars, destroyers of worlds, and the end of every story that crosses their paths. But what if we've been looking at them all wrong? What if instead of being the universe's final dead ends, black holes are in fact doors? Gateways not just to the end of matter, but to new physics, and perhaps even to the other side of the cosmos itself. Hold on tight, because tonight we journey to the edge of everything we know, where the laws of physics break down, and a new, mind-bending reality may be waiting to burst through. This isn't just a story about black holes, it's about what comes next. Are black holes truly the universe's ultimate trap, or the beginning of something stranger and far more profound? To understand just how radical this question is, let's rewind time. Black holes emerged from the math of Einstein's general relativity in 1916, when German physicist Karl Schwarzschild wrote down a solution to Einstein's equations. He described a theoretical object so compact that nothing, not light, not radiation, not even reality as we know it, could escape its grasp. The world had a new cosmic villain, the singularity, hidden behind a cloak called the event horizon. At first, even Einstein was unsettled by this possibility. He doubted such objects could really exist. But nature doesn't care about our discomfort. As astronomers peered deeper into the universe, the evidence for black holes mounted. The collapse of massive stars, as predicted by Indian physicist Subramanian Chandrasekhar, who calculated the maximum mass for a star's stability before it collapses into a black hole, set the theoretical stage. Then, in the 1960s, John Wheeler coined the term black hole, capturing the public's imagination and cementing these monsters into science and pop culture forever. Yet for all their infamy, black holes were long seen as mere mathematical oddities. That changed as our telescopes became more powerful. Observations of strange stellar orbits, mysterious radio emissions, and recently bursts of gravitational waves have confirmed that black holes not only exist, but are everywhere. In 2017, the Event Horizon Telescope snapped humanity's first ever photo of the supermassive black hole in the galaxy M87, a shadow against a fiery ring, the ultimate cosmic close-up. It was front-page news around the globe, and a direct challenge to everyone's picture of the universe. Here's the wild part. The deeper we look into black holes, the more bizarre the picture becomes. Some are just a few times the mass of our sun. Others tip the scales at billions of solar masses, lurking at the centers of galaxies like cosmic engines. They're detected by the matter spiraling into them, sometimes the most violent engines in the universe, blasting out jets of energy that stretch for millions of light years and outshine entire galaxies. The Milky Way would be a little dot in these two giant eruptions, remarks Martin Uwe of Caltech, marveling at the scale of these cosmic outflows. But black holes don't just gobble up matter. They warp the very fabric of space and time. Anything that strays too close, stars, gas, sometimes even entire planets, gets pulled inexorably inward. At a point called the event horizon, reality itself gets weird. Inside, according to Einstein's equations, all matter is destined for a point of infinite density, a singularity, where the known laws of physics break down completely. And yet, for all our mathematical certainty, two questions have haunted physicists for decades. What really happens to matter that falls into a black hole? And what, if anything, comes out at the other end? Einstein's theory gives a clear answer, sort of. It predicts the inescapable grip of the event horizon, the point of no return, and the singularity beyond. All information is lost, all matter destroyed, or at least, so it seemed. But in the 1970s, a young Stephen Hawking rocked the physics world by introducing quantum mechanics into the mix. He predicted that black holes would not live forever. Instead, thanks to mysterious quantum effects at the event horizon, they should slowly, ever so slowly, radiate away their mass. This Hawking radiation means black holes would eventually shrink, evaporate, and vanish, leaving behind a universe with no trace of what had been devoured. That's a pretty wild plot twist. Black holes aren't forever. But this only deepens the paradox. If black holes truly erase all information, then the laws of quantum physics, the same ones that govern every atom in your body, would be broken at the edge of a black hole. This is the infamous information paradox, and no one has yet solved it. The closer we look, the stranger the story gets. Recent observations, matter plunging into black holes at near light speed, jets that blast across intergalactic space, gravitational waves from black holes colliding, have forced physicists to confront these mysteries head-on. Andrew Mummery of Oxford University put it sharply. This final plunge of plasma happens at the very edge of a black hole and shows matter responding to gravity in its strongest possible form. That plunging region is now at the center of attention, not just for astronomers, but for anyone who wonders what happens to reality when pushed to its absolute limit. New technology is helping us probe these cosmic mysteries at an unprecedented level. With the Event Horizon Telescope, we see the shadow of the event horizon itself, a boundary so precise that nothing crossing it ever returns. Meanwhile, gravitational wave observatories are listening to the ripples from black hole mergers, providing exquisite detail of the otherwise invisible. But the biggest question remains: what lies beyond the black hole? Is the singularity truly the end of everything, or is it a puzzle waiting to be cracked open? That's where the cutting edge of physics enters the scene. For all its successes, Einstein's theory cannot explain what happens at the singularity. The problem is, gravity becomes so strong and space so curved that our best physical theories simply stop working. It's not just a mathematical glitch, it's a gaping hole in our understanding of the universe. To bridge this chasm, scientists need a quantum theory of gravity, a way to unite Einstein's equations with the strange laws that govern the subatomic world. And here, competing ideas are racing for the prize. One of the most promising is called loop quantum gravity, or LQG. Loop quantum gravity is an attempt to marry Einstein's smooth, continuous spacetime with the grainy quantum fabric revealed by brilliant minds like Niels Bohr. LQG suggests that spacetime itself is woven from tiny, discrete loops, not a continuous sheet, but a cosmic spiderweb with an atomic structure. What does that mean for black holes? In the LQG model, when a black hole forms and collapses, all the familiar rules hold up, until a critical point. At unimaginably high densities, quantum effects take over. Instead of matter plunging eternally into a singularity, LQG predicts a quantum bounce. The collapse is halted and reversed by a powerful repulsive force born from quantum mechanics. The black hole doesn't end in destruction. Instead, it rebounds. This is where things get downright mind-bending. That rebound, theorists say, could lead to the birth of a white hole, a time-reversed cousin of the black hole. In a white hole, nothing can enter, but matter and energy can erupt outward. It's as if the universe itself has an undo button, flipping the script on the deepest laws of reality. Can you picture it? At the end of its lifespan, after radiating away almost all its mass via Hawking radiation, a black hole quantum leaps into a new phase, a tiny, stable white hole. The event horizon doesn't vanish, it transforms. Matter and information once swallowed are not lost forever. They bounce back out, released as if from a cosmic vault. Niels Bohr's concept of quantum leaps, where electrons hop between energy levels and emit light, is echoed on a cosmic scale. Here, the leap is not just of energy, but of the very fabric of space and time itself. This scenario, bold as it is, directly addresses two of the greatest mysteries in physics. What happens to matter in a black hole, and how does a black hole die? In the LQG picture, the ending is not oblivion, but transformation. Of course, LQG is not the only game in town. Other rival theories, like the Gravistar model, which imagines a shell of exotic dark energy instead of a singularity, offer intriguing alternatives. But it's the black-to-white hole transition that has captured the imagination of physicists worldwide. Why? Because it offers, at least in principle, a solution to the information paradox. In this view, the universe doesn't lose track of its secrets, it just takes longer to return them. As wild as it sounds, this isn't just abstract math. The predictions of loop quantum gravity are starting to become testable. Advanced quantum technology may enable the detection of white holes, notes a recent research report. If we could spot one of these remnants, it would be direct evidence for the cosmic bounce, and the implications would be staggering. Not only would black holes be cosmic recyclers, but these white hole remnants, each barely the mass of a human hair, might even make up some of the mysterious dark matter that pervades the universe. But before we get carried away, the real world throws up more problems. For all the promise of LQG and white holes, no experiment has yet detected such a phenomenon. Not a single white hole has ever been seen. The universe, for now, keeps its secrets well hidden. And yet, the stakes are higher than ever. The world's top telescopes and gravitational wave observatories are scanning the skies, searching for clues. New discoveries, like the first black hole triple, mysterious jets spanning millions of light years, and matter plunging into darkness, force us to confront the same puzzles from different angles. What really happens as matter passes the event horizon? Could white hole remnants be hiding in plain sight, masquerading as dark matter? Or will a totally different model, perhaps involving dark energy or even undiscovered physics, win the day? So here we are at the edge of knowledge. Black holes were once science fiction, now they are science fact. But are they the universe's deadliest dead ends, or its most tantalizing new beginnings? As we look forward, the answers may upend everything we think we know about space, time, and the fate of the universe itself. But there's one more twist. If loop quantum gravity is right, and if every black hole eventually becomes a white hole, what would that mean for the ultimate fate of information, matter, and even life in our universe? And could the tools we have today finally reveal the first evidence of these mysterious cosmic bounces? The search is on, but to get closer, we have to tackle the hardest questions yet, questions that may force us to rewrite the laws of physics as we know them. Now let's travel to the heart of the future, the frontier where imagination, mathematics, and next-generation technology converge. The question burning at the center of this cosmic story is bigger than black holes themselves. Are we on the verge of finally witnessing a black hole bounce into a white hole, reshaping everything we know about reality? Let's picture the universe not as a smooth, unbroken canvas, but as a pitted, turbulent sea, constantly reshaped by black holes punching holes through space-time. Thanks to Einstein, we can trace the edges of these mysteries, but it's quantum physics, more specifically, loop quantum gravity, that teases us with the wildest possibilities. You might wonder, what happens if we actually truly confirm that black holes can bounce into white holes? What would it mean for physics, and for our understanding of time, space, and our own existence? To answer this, let's first consider the stakes. If loop quantum gravity is correct, the black hole's death isn't an end, but a transformation, a quantum leap. After billions of years emitting Hawking radiation, shrinking and twisting in on itself, the black hole hits a point where quantum effects dominate. Suddenly, instead of shrinking out of existence, the process reverses. What was falling inward now rushes out in a white hole explosion. According to calculations, this bounce wouldn't be some grand, star-destroying event visible across galaxies. Instead, most of the original energy would have already drifted away as Hawking radiation, ancient, cold. What's left is a remnant, a white hole with the mass of a microgram, a speck with the weight of a human hair, yet potentially holding the secrets of everything that once fell inside. The tantalizing possibility? Matter and information might not be lost forever, but could eventually escape, through this tiny white hole, back into the universe. This would resolve the infamous information paradox that has troubled physicists for decades. As Oxford physicist Andrew Mummery puts it, this final plunge of plasma happens at the very edge of a black hole and shows matter responding to gravity in its strongest possible form. It's this edge, the place where Einstein's deterministic universe meets the wild unpredictability of quantum physics, that may finally yield its secrets. But here's where the future intrigue really heats up. What are the practical consequences if we prove black holes bounce? First, it would mean that space and time themselves are quantized, broken not into smooth distances, but into discrete, smallest possible pieces, as loop quantum gravity suggests. Imagine space-time as a digital image, not a perfect photograph, but a pixelated mosaic. The entire universe would be ruled not by continuous laws, but by quantum rules. Such a discovery would force physicists to rewrite textbooks, upend old dogmas and mathematical frameworks, and perhaps even provide the long-sought link between general relativity and quantum mechanics, the so-called theory of everything. But it gets even more wild. Some theorists suggest that these long-lived white hole remnants could be hiding all around us, relics from the evaporation of primordial black holes early in the universe's history. Could these ghostly objects be a component of the mysterious dark matter that makes up most of the universe's mass? If so, the implications would be staggering. Not only would we solve the fate of matter inside black holes, but also unlock the origin of dark matter, one of cosmology's greatest mysteries. Suddenly, the invisible scaffolding holding galaxies together might be made not of exotic particles, but the leftovers of long-dead black holes, tiny white holes, scattered across the cosmos, completely invisible to us. Yet, as with all frontiers, new mysteries would emerge. What happens to information as it tunnels out of a white hole? Could it ever be retrieved, or is it scrambled beyond recognition? Would the outpouring of matter and information be gentle, or could it produce detectable signals, stealthy flashes of radiation or ripples in the very fabric of space, waiting to be caught by our most sensitive instruments? Martijn Uy of Caltech points out the awe-inspiring scale of black hole jets, stating, "The Milky Way would be a little dot in these two giant eruptions." Just as jets from supermassive black holes shape entire galaxies, perhaps the bounce from black to white holes could send shock waves, literal or metaphorical, through our understanding of physics. So how close are we really to proving or disproving this bounce scenario? The answer may lie just around the corner. The recent imaging of Sagittarius A by the Event Horizon Telescope and the detection of gravitational waves from black hole mergers have given us glimpses of the extremes of physics. But what we need is more. Next-level telescopes, quantum detectors, and the ability to monitor even fainter signals. Enter the James Webb Space Telescope and the next generation of gravitational wave observatories. Armed with these tools, astronomers hope to catch the faintest whispers, the cold Hawking radiation, the quantum echo of a black hole's demise, or perhaps the blip of a white hole's sudden appearance. If white holes exist, and if information does indeed escape, then sooner or later we should see their fingerprint. Consider this. If we detect a flash, a burst of radiation, or an unexplained gravitational wave signal that matches the predicted signature of a black-to-white hole transition, the implications would be seismic, not only for theoretical physics but for technology and philosophy. Which brings us to a crucial point. What practical benefit could all this possibly have for you here and now? First, understanding the ultimate fate of black holes isn't just a puzzle for physicists. It's a living experiment at the very foundation of our universe. The same quantum rules that might cause black holes to bounce could one day be harnessed for technologies we can barely imagine. Quantum computers, sensors that read the tiniest ripples in space-time, or even propulsion systems inspired by quantum gravitational effects. In a more philosophical sense, black holes stand as a mirror to our own limitations. The quest to understand their true nature pushes science to its ultimate edge, forcing us to invent new mathematics, pioneer new instruments, and confront our deepest questions. Is reality fundamentally deterministic or random? Is information ever truly lost? Are we, as conscious beings, part of a universe that evolves predictably, or does it harbor infinite surprises? The story of black holes is also a lesson in curiosity, a reminder that the universe always holds more secrets than we expect. If a black hole can bounce into a white hole, then even the most hopelessly trapped things, energy, matter, or information, are never truly lost. There's always the chance for a second act, a cosmic comeback. That's a powerful metaphor for resilience, reinvention, and the relentless forward march of discovery. Here's how you can tap into this cosmic adventure. Stay curious, follow developments in space science, and never underestimate the power of asking impossible questions. It's this spirit that has driven humanity from stone tools to gravitational wave detectors, from myths of the night sky to photographs of black holes themselves. And now, for the big reveal, a secret fact that even most space fans don't know. While we've never spotted a true white hole, some astrophysicists believe that certain unexplained bursts of energy, fast radio bursts or FRBs, could be the explosive sneeze of a tiny white hole remnant, suddenly releasing its trapped contents into the cosmos. If this connection is ever confirmed, then the next mysterious blip picked up by a radio telescope could literally be the dying breath of a black hole, transformed and reborn on the other side of physics. So, after all this cosmic detective work, can black holes really bounce into white holes? And will we soon prove it? The best answer, as of today, is maybe, and sooner than you think. The theory is ready, the technology is finally within reach. The next decade could hold the answer, and with it, a revolution in our understanding of reality itself. If you're as captivated by this mind-bending journey as we are, there's never been a better time to follow black hole research. Subscribe to our channel for the latest updates on astronomical breakthroughs, quantum oddities, and everything in between. And the next time you gaze up at the night sky, remember, the universe is filled with mysteries as strange as any fiction. Somewhere out there, a black hole may be making its final leap, rewriting the story of everything we know. Curious for more?